All right. Hi, everybody. Thank you for joining us today. This is a session on cloud data optimization, particularly focused on emerging best practices. And this is really a follow-up from the workshop, a similar workshop that we hosted last year at the summer Unzip meeting, focused on the same subject. So we have an interesting dynamic at this session. We have 9 presenters in 90 minutes roughly, but the good news is that we actually have 2 sessions. So this is really a workshop that includes 2 sessions. The first one is focused on providing a very quick overview of some of the work that is being done out there in the space of cloud data optimization. And the second one is more of a roundtable where we'll be mostly speaking and trying to identify some of those emerging best practices. Before I continue, just a quick introduction. My name is Ana Pinheiro-Privet. I'm with the sustainability team at Amazon. I'm a senior program manager. I'm also the lead for a program that Amazon launched last December called the Amazon Sustainability Data Initiative. And we work very closely with some of our partners inside of Amazon, from the open data team on AWS, and Joe Flasher is here and is one of the co-moderators for this session. I would also like to acknowledge Jeff DLB, who is online. Unfortunately, wasn't able to be here in person, and is at NCAR and is very interested in working with us on this subject of best practice for cloud data optimization. Okay, I'm kind of working fast and talking fast because we do have a very full agenda, and we have 9 outstanding speakers today. I believe so, and we're very grateful that they agreed to come to the session today and share some of the work they are doing. Just in terms of logistics, because we are so tight for time, everybody has about 10 minutes. We're going to have a break for coffee in between, and then we'll come straight up back and go into the discussion. Annie had kindly offered to be the dictator with the time. We really have to do that. So she'll be giving you a 5 minutes, a 2 minutes, and a, time is out warning. And we are going to, I put this up here because these are some of the questions that we would like to bring to the discussion in the second part. And so I would like to encourage you to just keep this in mind as we go through this process and through the conversation. And so the goal here is trying to understand what are we seeing in terms of best practices for hosting data in the cloud and make it more easily discoverable, accessible, and usable? And what are the things that we need to do moving forward to enable better clarity in that space? So is there anything that we are seeing that is already working for the majority of the people? If not, do we have to do more experimentation? Is it helpful for us to start documenting the status of this landscape? If so, what is the best way to do that? And Annie is here also representing Unzip, who is very interested in being part of this process and perhaps the umbrella for that conversation. So I'm going to step aside and ask Dan from Element 84 to come forward and give us 10 minutes presentation.
The screen is not being shared currently.
Okay, let me see. Okay. Yep. It did earlier. Yes. Okay. This doesn't come out of my time, right? Okay, all right. Okay, I promised Anna I would fit this into 10 minutes, so good luck. All right, I'm Dan Pallone. I'm going to talk about Stack. Stack is the spatiotemporal asset catalog. Before I dive into this, I'm going to be talking some about metadata. Metadata tends to bring out complex emotions from people. Please do not shoot the messenger. I am a metadata pragmatist, and so this is something we should be looking at, but I'm not here to start a war. Please don't blame me. All right, so let's just go with the elephant in the room. Why am I even talking about this? Why do we need, yet another set of metadata? Kind of what's the purpose? The point of it is it's still hard to get to data. It is still complicated. Depending on what you're looking to do, what data you want to use, what agency, whether you're using commercial data and open data, depending on where you're going for this, there are multiple clients you need to hit that all kind of do something similar, but you need to learn those clients, you need to learn how to interact with those clients, and you need to learn the data and how they're going to get you that data on the other side of it. On the API side of the world, it's a little better. There are some standards in APIs. But they're not all using the same standard, and they're not all using it the same way. So a fun one to pick on is always cloud cover, right? Cloud cover could be 0 to 1. If you're searching for a piece of data, what's the cloud cover in that scene? It could be 0 to 1. It could be in percentage. It could be 0 to 100. We've seen some where it's actually written out. It's little, none, a lot. And so all of this ends up landing on the user and they need to kind of figure this out in terms of how to get to the data. So Stack really comes at this from the search and discovery side of the world. I want to real quick, that disclaimer at the bottom is really important. This is not an official Stack statement. I have no authority with which to speak for Stack, but the way I think about it is Stack is really looking at increasing the interoperability of searching for data by enable global indexing. So you can kind of think about it as kind of how the World Wide Web has evolved. You have web pages. There are different search engines out there that are crawling these things, indexing them, exposing different capabilities, indexing the parts they're interested in, ignoring the parts that they're not, prioritizing differently. That's kind of the model that Stack is trying to set up. So at high level, what is it? It's really three parts. There's three pieces to Stack. The first one at kind of the bottom of that stack is the metadata model. There is a metadata model associated with it. It is small, it is simple, it is designed to be extended, and it is targeting search and discovery. Sitting on top of that is this idea of static catalogs. So when this all started, there was this kind of discussion around, how do we increase interoperability? And one of the easiest ways to make APIs interoperable is just to get rid of them. And if you think about things like, S3 or just kind of direct file access over the web, if you can make an HTTP request, you can get data back. So if we can give data back, if we can give metadata back in a format that's usable, you could potentially crawl the holdings. You could move through this metadata as long as you can understand the metadata with just a simple HTTP request. It's not for everybody, but it starts there. Then layered on top of that is this idea of a Stack API. The Stack API is WFS3 with extensions specific for Stack. But the key thing is the results you're going to get back from that API are exactly the same as the results you would get back if you were just crawling the underlying metadata items, if you were to hit it through the file piece, which means that a really simple client just making HTTP requests can find and traverse a metadata hierarchy to find the items they want. If you're a more sophisticated client, you can speak WFS3 and provide search parameters and filter parameters. You can do that too. At the end of the day, you're going to get the same set of information. What it is not a full-fledged metadata standard. It is not intended to be a single source of truth. It is not trying to cover all the data sets in the world, and it is not a replacement for ISO 19115 or CSW spec or anything like that. It is intended to be search and discovery and make that data available. It does not replace the provider metadata, and it is not an excuse to talk bad about me after I'm done this talk. It is intended, you can take original provider metadata, you can make it available in Stack, convert it to Stack, map it into that, make that data available, and use that for search and discovery purposes. But that provider metadata is still essential. It is not a provenance kind of a metadata approach. So brief history of what this thing looks like. It's just under 2 years old, originally starting out October of 2017. You can see as you kind of progress, in April, the WFS3 piece was added. Moving forward, collections came up in 0.6, and then Tsar, Point Cloud, and Datacube extensions all came beginning of this year. The goal is 1.0 at the end of this year. Now, something to point out, Stack takes a different approach to versioning and to kind of when things get rolled out. It is implementation based. So if you think of kind of a traditional specification model where there's a lot of iteration on the spec, there's a lot of discussion around what that standard should be, it reaches a point where it's then approved and published, and then it is put out there and implementations are made based on that. Stack takes a different approach. Stack goes at this with, we're gonna build out things that we think work. Each of these are considered sprints. We're gonna build out something that's useful. When those things are used, when it's accepted kind of at critical mass, then it gets adopted into the spec. The spec gets incremented by a version number and it's out there. But the idea is that when it's in a spec, there are people using it and it's demonstrating value before anything ends up in there. And so 1.0 is targeted into the year. It'll probably slide into Q1 of 2020. But again, it's really implementation driven. When the pieces that are surfaced in 1.0 are available in enough places, the version will get bumped. Kind of who's driving this? This is a collection. The original one was, I think it was 14 groups, or 14 different organizations / companies represented to help create this. Again, they run in sprints. And so what you see here, this is a slide shot of logos of people who are sending people out to wherever that sprint is for an actual implementation period to build a piece, release it out. It's all open source. It gets pushed out there, and then that continues to repeat with those. All right, what's the spec look like? I've got a bunch of eye candy at the end, so I'm gonna get through the deep stuff and then I'll show you some pictures. What's the spec look like? At the top level, there's a catalog. There's always a root catalog. This is basically your entry point into some set of metadata that you're looking at. That catalog can contain other catalogs. It can link out to other catalogs, or it can link to collections. Collections are the next tier down. When you get to collections, they may also contain catalogs, subcatalogs, or they can point to other collections, or generally they contain items as you work your way down. So you could use this structure, for example, to take Landsat, which is path row based, and you could create subcatalogs at each of those levels, and somebody could enter it wherever they want to enter into that hierarchy, grab that catalog at that path, and then have access to all the row data underneath, or just jump in further on. When you get down to the bottom, you get to items. Now, again, going back to that interoperability, everything is JSON based. And so the items are actually GeoJSON features. So anything that can open a GeoJSON file can open a stack item and see that footprint, visualize that footprint. Whatever they can do with a valid GeoJSON file, they can take advantage of it. And then that item links to assets, which is the actual underlying data, the imagery, the scenes, the thumbnail, whatever else happens to be in there. Quick look at the API. It's really this simple. WFS3 compliant with extensions. I mentioned that. All right, so now I'm going to shift over to the ecosystem, and this is where it gets neat. So Stack Spec is out there. Again, there's implementations for it. I'm going to show you some of those examples. This is the Stack Validator. This is hosted at StackLint. You can also get it off GitHub under Stack Validator. The URL is there. But this is just a simple tool that can go ahead and actually validate the Stack JSON. It's using a JSON schema. It can actually validate that the fields exist, and it's a high-level piece, but it's an example of something there. This is a Stack browser. This, if you can see that URL at the top, that's actually just an HTTP URL pointing to a Google storage. And that's pulling a static catalog. And so what you're seeing here is navigating all the way from a top level. So when Planet puts out disaster response data, they make stack catalogs available for the response data they put out there. And what this can start at the top level, pull that initial top level catalog, and then just give you a view where you can just click through this. There's nothing back behind this. There's no API that it's hitting or anything along those lines. You're just working your way down. Oops. This is a QGIS plugin. Again, it's a real simple plugin that can reach out, talk to a Stack API, work your way down. Eventually you get to an item. Because the item is a GeoJSON file, it can actually go ahead and display that footprint. It can also fetch assets and then let you visualize those assets. This drives all the way down into using QGIS, but again, interacting directly with the Stack metadata and working your way through. Now, if you want to get even closer to it, there's a whole suite of projects called Undersat Utils. That's an umbrella project. Undersat Utils, the time's like flying here, so I'm gonna keep going. The Undersat Utils, you have Sat API. Sat API is a project that you can use to spin up an instance of the Stack API and expose it out there. It can crawl static catalogs, index those, and then it surfaces all the searching capabilities. So an example of that is we deployed Earth Search, which is running in AWS, and we've pulled in the catalogs from the public data sets. So you can hit this, exposes the API, and consume it. An example of doing that is the Sat API browser, also available under the Sat Utils project. This is hitting that API, or able to hit that API, and traverse down through the metadata hierarchy and get there. If you want to create metadata, Sat Stack. It's a Python library that can interact with Stack metadata. Create the metadata, pull it back. This is what's used to create the Sentinel catalogs, to create these Landsat catalogs. You can take a look at these. It's just basically fetching from the original metadata source, mapping it into Stack, and pushing it out. All right, I'm going to jump to the, before I get chased off stage here, the Sat Search. Sat Search is able to interact with it at the command line, the API, which leads to Sat Fetch, which pulls the actual data. And with a command like this, and the underlying cloud optimized data, it can reach out, because the data is separated by bands, it can pull the bands by name, it can use the geospatial area you can provide in a GeoJSON file, extract that, use GDAL to do the subsetting, and create a geotiff of this layered data of each of the bands that you pulled out. This is Landsat, this is Sentinel, and I'm done. We can talk more this afternoon. or later.
Thank you. Thank you. Okay, next we have Hamed with the Radiant Earth Foundation. Annie, is there any way to get this out of the screen? Does it need to be visible? It doesn't, right?
No, it doesn't.
Okay. All right, thank you.
Oops. Not backup slides. Okay. Hello, everyone. My name is Hamid Al Mohammed.
I'm gonna do a really here. Stop that. Let me make sure there's no one that is.
Okay.
Test. That was it. All right.
Debugging. Okay, I'm not going to touch this. Sorry, it should be on the first slide. Yeah, this is Hamid Al Mohammed. I'm the Chief Data Scientist with Radiant Earth Foundation. Just for those of you who might not be familiar with Radiant, just one slide introduction. We are a nonprofit organization based in US. We work on the intersection of with the recent pivot on machine learning and Earth observation to address global development challenges. We are funded by the Gates Foundation and Omidyar Network, kind of philanthropic organization in this space. And our mission is really how can we have better tools that would enable those users to benefit from these applications. And one of the very key focuses that we have now is on open sourcing training data with remote sensing data that can enable better and enhanced machine learning applications. Just as a motivation, thinking about particularly the agriculture and land cover application that we have now, these are just sample representative examples of the diversity of agricultural patterns globally. Sometimes we think about it, but we don't visualize them and recognize them that there is a huge diversity and geographical diversity in particular in these patterns, along with a lot of farming practices and things that goes into that. So if we want to have machine learning applications that can monitor these tools, that can provide recommendations to the farmers, that can have a kind of base statistics layer to the governments and decision makers, we need to have training data, meaning a set of satellite observations and ground reference values that are representative of that diversity. Otherwise, our models won't be doing a good job. What's happening in this space now and how we are targeting it is that, think about it of two groups that are trying to build a machine learning model using Earth observation. They go generate their own training data, they do their own training, they build a model, and they do prediction. As a user, you can benchmark the models against each other because they are trained on different models. And there is no way to reconsume that training data. It is happening, but maybe 5%, 10% of the community. 90% of the community is redoing this. We just heard in the session at noon that more than 60% of researchers' time and developers' time goes to data preparation. And that's the same philosophy here. We don't benchmark and catalog training data. We just talked about the actual remote sensing or Earth observation data, but the training data is the same philosophy. That's the ideal workflow that we are thinking we should go. We have those benchmark training data sets cataloged well using a stack. I'm going to show that now. And also in a standard way that the community agrees on. And then at the end of the day, we can benchmark the models against each other. So we know which model is doing better, and we can progressively improve those models and applications. We have been working with particularly the agriculture and land cover community around these aspects, and we are going to host events specifically around that. But what Radiant provides as an organization is a hub to share and expose those data. The hub is called Radiant ML Hub, basically. And it is not supposed to be that, oh, all the data should come to us. No, I will show you the architecture. It is basically a discovery tool, and that's enabled by Stack. So people can come, call an API, see what training data is available so they can consume it. We will also try to get into benchmarking models down the road. After we have those training data, we can also think about how can we benchmark models. When we have a good machine learning model using all of these data, how we can share them, and then potentially running some competitions around that. The other aspect of Radiant's work is in building a community around this. So it's not just the tool that we provide, we work with the community. The Stack story that you heard, one of our technical fellows, Chris Holmes, basically leads that effort, and we have been very happy to work with all the commercial and government and private basic nonprofit sector to come up with that standard. So that's part of the work that Radiant does as well, and also doing education in the global development sector around the recent advancements in this space. So you just heard about the Stack, and Dan mentioned that Stack has extensions, and one of those that was very recently accepted to go to the main pipeline is a Stack for training data. So when you have a basically set of imagery and labels, whether it's an annotation coming from the imagery or it's a ground reference data coming from surveys and by basically groundwork, you can catalog them in a Stack catalog and making it the standard and expose them through the similar API. This is now available on the GitHub branch and under the dev branch, if you're interested and you're looking into that. But this is what the ecosystem on Radiant ML Hub will look like. So the mouse is here, yeah. So the good thing with the Stack is that you don't need to have the data all in one location. What you care is all the catalogs be exposed to the API. So Radiant is going to host all these catalogs, that is training data generated by Radiant or generated by others. So some of the data is sitting on Radiant's storage, and some of the data is sitting on other cloud storages or data providers. What we care about is all of them are under Stack catalog, and all of them have a good quality standard in terms of being shared and exposed with others. We are providing a ML Hub API. This is not public yet. By end of August, we hope we will make it public, and it will be basically open access to everyone. There is some authentication happening just to know what's going on, who is using what, so we get some statistics about the usage of the data. But otherwise, all the data will be basically open source license. And then there's a public API endpoint, and then a Python client at the end that I'm gonna show you a snapshot how it will work, and a search website for those who are just interested to see what is out there. They don't necessarily wanna get into programming. My dream is to come to this point. It will be probably 6 months, but is import ML Hub, define bounding box, shoot some keyword like maze and the bounding box, get the data and say load the data, get it in your Python. This means all the imagery and the labels in your Python environment live. Probably it's running on a cloud. You don't want to get all of those in your PC or laptop memory, but that's where we hope to go. And this is where a benchmark can happen. So from this point on, the innovation happens, the change happens, people start building different models, but up to here, everything is benchmark, everything is similar. So we can think about, okay, what is missing? We can try 10 different models and see, oh, maybe we are missing actually some training data. We can then go back and build more training data. This is not on pip yet, so don't try to do pip install ML Hub. Let me show you an example of the Stack browser that Dan just showed, but for training data applications. So Stack browser now supports training data, and this is from a colleague from World Bank, Dave Liu, who showed me. So these are labels and the imagery in the back. So you're basically, and this data is being streamed live from the source now. There's nothing local. I'm just in the browser. That's the beautifully of the Stack browser thing. You're streaming the imagery, which is in COG format. So that's the beautiful of the cloud optimized GeoTube format. And then the labels are just GeoJSONs, and this is the Stack catalog streamed out. You can start visualizing and exploring what's happened. You can look at the thumbnail and all of the other assets that potentially listed here. Depending on the application, you might have other assets listed here. This is more on the visualization side, but from a search side, you will call the API basically. And then, so these are the two data sets that Radiant is working on currently. We are working on a land cover training data set, which is crowdsourced based on the Sentinel 210-meter resolution, globally, globally representative. We want to make sure there is representative samples from all the land cover types globally. It will be hosted on AWS, the resource that you just saw. And then another one is the agricultural crop types, particularly in Africa. We will start with Africa, but we want to expand to other regions And these are the labels that come from ground surveys, referencing national statistics that come from governments, and we catalog them, clean them, put them on top of imagery, and publish them as training data. And here, what we mean by training data, particularly in agricultural applications, I put the image at the bottom. It is a time series of imagery. It's not just one image and label. That's maybe good for object detection, but when we think about agricultural applications, land cover applications, we have all the data. We have every 5 days a Sentinel-2 image, so we want to use the time series. So the type of training data here is a multispectral data over time, 4-dimensional data basically, with a label at the end. That's how we think about them. And I appreciate the sponsorship from Schmidt Futures and McGovern Foundation for these two. That's all from me. Join the community, try to share your data, speak out about it if you have thoughts. Would love to hear about them in the next session. Thank you.
Thank you, Hamid. Now we have Grega, and I want to thank Grega. He's probably the one that came the furthest, at least for our session. He came all the way from Slovenia, so thank you.
So I'm Grega, I'm coming from Slovenia, as told. Anyway, we've been talking a lot about the data formats here in the previous sessions, and we'll be hearing more about them later on. And there is a lot of question which one is the best format, right? Is it the cloud optimized GeoTube, or is the HDF, or it's Tsar, or something else? And because I believe that this really is not the answer that we are looking for, we should rather be looking for how the data should be structured. And then I think that the software can simply adjust to different kind of formats. And this is what I'll focus to these presentations. And what I think that are the most important factors when talking about the data on the cloud is, first of all, that they are easily readable, meaning that there is a driver out there, supposedly or hopefully the open source, so that you can read it. And then it comes to basically the costs and the performance, right? How much it costs to store it, to how much it costs to process it, how fast it is because of the users. And at the end, it always comes to the point that you want to have access to the subset of the data. As soon as you need to read the whole thing, it's usually simply too slow. Now, we've been working mostly with Sentinel data, so I'll be focusing to the experience we gathered working with Sentinel data. And I'll start with the simple step that everyone needs to do is first to gather data to the cloud. I think that's the first thing that you need to do, whoever is hosting or having the data. And putting the data on the cloud means that the data are accessible within the cloud. I think that if you put it on, I don't know, AWS, and then you put like an interface in front of it, either the user interface or a very complex API, you didn't do much of a benefit, because usually that thing will not work good enough. And it will be slow. Then the second thing, when you put the data to a cloud, unzip it, right? Because if we want to work efficiently with the data, it needs to be ready to be read. And as soon as it is zipped, we will have to simply download it from S3 to the virtual machine. And I mean, what the point did we then make putting it on the cloud if we still need to download it? Now, going into the specifics of the Sentinel-2, first, the good things is that the JPEG 2000, which is used in Sentinel-2, is actually pretty good format in terms of the cloud. It doesn't have the best driver out there, which is open source. I mean, OpenJPEG is open source, but the best one is Kakadu, and that's not open source, unfortunately. But every other elements of the JPEG 2000 are really just fine for working in the cloud. Now, in terms of the bad things, I did quite some mistakes. First of all is the precinct, or the minimum tile, which also comes in the cloud optimized GeoTube. If you use the too large precinct or internal tile, that means that we'll need to read too much of the data which we don't need, and this will be slow, and this will be expensive, and this will usually require a lot of memory. And on the other side, if the tiles are too small, then it will probably need too many reads. And now, if the data are on requester paste bucket, which Sentinel now are in Amazon, that is even more so expensive, because every read costs something. And if you do billion of them, this something is actually something that you pay quite a lot. Now, I think it's not easy to define the best size, but because you need to kind of manage the how many reads you need to do, how much data you process, how much it costs to uncompress, and so on. But based on our experience, I think like 500 by 500 pixel or 1000 by 1000 pixels is probably there somewhere, but it probably also depends on the use case. So then we have the metadata, which was mentioned already, and like we have metadata like the sun angle for Sentinel-2, and these are conveniently stored in XMLs. And as we heard in the past session, the XMLs are something that people don't really like. They're also something that are slow to read. So if there are data which can be stored as raster, they should be stored as raster because they are much faster. And then if you have rasters, like we have scene classification in Sentinel has about 12 values, and yet they decided to put in a 16-bit raster, which is for 65,000 values, and obviously it's way too large and requires lots of memory. So think about what kind of depth is needed to actually support some specific format. Then there are specifics of the JPEG 2000, specifically the wavelet transform, which is not really best for the discrete values, because then when the borders between the some values, you'll actually get a third value, which is not something, it's not an average between these two, right? So for the discrete values, I think the cloud optimized GeoTIFF is better because then you can control the layers better. And now in a bit of the management aspect, whenever the data are processed, there should be a version of this processing software somewhere written in the metadata again, so that we who use the data know what to expect. The worst thing that can happen is that the processing software changes, and then you notice this only when your program crashes, which ingests the data. And this happens a lot with ESA, unfortunately. And then we tell them that this is not a good thing, and say, oh yeah, but this is an unimportant change which doesn't affect the user's quality. Well, it affects us and probably all the others who are ingesting the data. And talking about the changes, think about which changes are really needed. Like there is a guy who changed the folder from granules to granule because it was nicer, right? But again, it crashed the ingestion process for many people, and that's simply not good. So change only whenever something is actually necessary. Then going to Sentinel-1 GRD, a good thing is that it's a GeoTIFF, so that's a nice thing. The bad thing is that it's not cloud optimized, far from it. It doesn't have the internal tiles, it doesn't have overview files, and the header, so that you know where something is in the file, is at the end of the file. So you need to read everything to find out where you can find something. And if you're looking for just a specific set of data, you'll need to read about 100 times more than what you actually need to read to get that, because it's not cloud optimized. When we moved this to, well, when we created a replication on Amazon, we changed it to cloud optimized GeoTIFF, and we actually gained about 15% storage, so it was less storage needed than before, with all the overview layers and so on, and it was much more usable for the users. I told previously that we need to unzip the data. Obviously, there are cases when zip files do make sense. First one is if you want to support the further replication of data. So like on Amazon, when we copy the data from the hubs to Amazon, there is a folder for the zips, which I think is like a weekly archive, rolling archive, so that others who want to replicate further on can simply take the zip files, not the individual files. But for everything else, it's not really needed. Then there are some data sets where actually it does make sense to keep it in zip, like Sentinel-1 SLC is such, because the zip file is about 5 times smaller than the original. And when you are working with the SLCs, your process is so complicated that unzipping your file in the meantime will not change anything at all. So you can do it. A lot of the discussion is going how far we should go with the analysis ready data. And our opinion is that we shouldn't go too far, because whenever we do some adjustment in that direction, we make some assumptions which are good for a specific user group, but not okay for many others, and this will actually make it worse for others. So and also when we are doing that, we are putting some money behind it, which maybe would be better spent in other way, right? Like extending the archive. So our recommendation is that when moving to the cloud, we only do the things that are necessary for the vast majority of users and that do not impact the quality. Everything else can be done later on with services like ours and many others, which can do all these things like analysis ready data on the fly. I skip this. As an example of how these things can work, I'll invite you to test this bring your own data functionality of the Sentinel Hub, where you can put the data at the moment in the cloud opening as Geotube to the Amazon, and then register it with Sentinel Hub, and you'll get all the analysis ready data functionality directly through the service without doing anything in that direction. And there are many people who say, yeah, that's fine, but it's slow. It's not that slow. I mean, it takes less than a second, usually half a second, to get a result, which is just fine for many cases. And then others say that it's expensive to do it on the fly, but it's even more expensive to do it in advance without knowing what actually you need. Like, it costs about $60 per 1 million square kilometers processed with Sentinel Hub, so it's really not that expensive. Anyway, what we would like to move to see in the future, first of all, is that USGS finally moves the Landsat 5 data to Amazon. This is what we are asking for the last few years already. And then when you are moving the production to the cloud, make also the intermediate products accessible to users, even if just for a period when they are available, because this would actually make it possible to do some near real-time applications on top of it, which would be very good for the end users. And when you're doing this step, do take into account that the satellite data are no longer just for research, but are actually production used, and you should treat it such. So that means that it should be also, the ingestion process should be run as an operational process, and whether things are not working, you should simply say to the user that they're not working and my time is out. So thank you very much.
Thank you, Greg. We now have Hon from Esri. Yep, great, thank you.
So how to work, find the file.
Let's see. Should be here.
Yeah,
This one, I think I misspelled your name, sorry. Okay, good. There you go.
Thank you, Anna. Hello, everyone. I'm Hongxu from Esri, and my colleague Sudhir is also from Esri DC office. So I'd like to start with this slide to introduce what we do and the background of this topic. You know that ArcGIS is a suite of software packages by Esri that used in many applications. And I work for a development team that develop imagery capabilities from supporting imagery types, scientific data, processing imagery, analyze, and raster analytics in the cloud. So it's basically the capability across the platforms. And this particular topic, multidimensional CRF, is one of the features that we have been working on to support multidimensional data. So it's basically, I represent our team to present this capability. So we support quite a wide range of data, from simulation data, forecast data, and many types of EOS data. Some of the data stored as NASDF, GRIP, and some like EOS data stored as TIFF and HDFs. These formats have advantages in managing the dimensions, managing many types of data, many variables stored in one file. However, when it comes to analysis in a cloud environment, it's not performed, it's not very efficient. So especially when the data volume become large, spatially and temporally, like large time series data, long time series data. So we need to find a better solution. And this is the multidimensional data model in ArcGIS. And we have this multi-raster object, and it contains one or multiple variables, and the variable is 3D or 4D arrays defined by the dimensions X, Y, time, and depth, and the pixels can be one or multiple bands. So this is very much like a NASDF data model, and we can create this object directly from these formats. And if it's like a single format, if it comes as multiple formats, like EOS data, a collection of scenes as TIFFs, HDFs, or like multiple NASDF files. So we have this mosaic dataset data model to actually catalog it is a table that indexes the metadata of the images, the raster. And we actually do not write pixels for this particular data model. We basically reference the pixels. And when we open it, it creates a multidimensional raster object on the fly. And multidimensional CRF, this is actually the main thing that we want to cover today, is a new format that it is store pixels, and it is we call this persistent image cube. And so regardless, it is an SDF or mosaic dataset or multidimensional CRF, and we have very easy to use user interface to work with it. Like if you're familiar with Python, and we have this ArcPy user experience, like you can open any of the data as a multidimensional object very easily. So because the multidimensional CRF is created from the mosaic dataset, so I'll talk a little bit more about the mosaic dataset. This is the Landsat service that is actually created from the mosaic dataset. This backend mosaic dataset manage all the Landsat scenes, the whole collections, and when new scenes comes in, it update automatically. We have this mechanism to update the scene, update the mosaic dataset, update the service. And this service support, you can query scene by the time, you can get a product like color infrared, vegetation index, and moisture index. So the point is that you can get many product on the fly processing product, because we don't store this copy of this data. These are configured, and you can process on the fly. You get this product on the fly. And another example is recently we work with NASA US team, and we work with their own because they built open data cubes, Africa open data cubes. So then we create mosaic dataset by ingesting the data in Amazon cloud, and then build a service. This is the Sentinel-1 data. So the mosaic dataset, the service is really powerful, that you can manage data easily, update data easily, and support on-the-fly processing. However, when it comes to analyze multidimensional data, a lot of long-time series data, and it has limitations. So this is why the reason of multidimensional CRF come into place. And this multidimensional CRF is obviously optimized for distributed computing in a cloud environment. Also, it actually in a local device. And the structure is folder-based, and one folder contains organized by the bundle binary files that contains many tiles. So the tile is the basic unit for processing and the compression and things like that. So when we're dealing with multi-dimensional raster, so we store it one variable per folder. And in addition that, because we want to support long-time series operation like probing operation or temporal profile, so we store actually a copy of the cube by flipping it. So we call it transpose. So it is support fast temporal profiling operation. And so this format is very efficient in performing the multidimensional computing. So from other sessions, we talk about the slicing, probing, subset, aggregate, and those type of operations. In addition, this format and the multidimensional data model support, we call the, if you're familiar with map algebra, this cube-based, so it's a cube algebra. If a math formula have different input, the output is a cube. So this is a few examples. This is a CRF used by RAS analytics in cloud, large image collections, a lot of pixels, and we use Amazon service, 10 instances, each one is 20 cores, and then anyway, so processing fast. And another example is the multidimensional. We create sea surface temperature from this 35 years monthly data is the anomaly, so created in multidimensional CRF format. And this is another example of we do calculate the regression model for each pixel along the time. So then this is the coefficient. It's actually the slope of the trend. It shows where is increasing, where is decreasing. And last but is the most important thing that I want to show you. It is the long time series multidimensional CRF. It is created from 35 years of data. It's daily data. So total time slice is 12,775 slices. So if you do this temporal profiling operation in my laptop, it's 3 seconds. And if it's on a S3 device from the internet, it's about 6 seconds. So the performance. So we basically use the storage to trade off the storage for better performance. And this is the end of my talk. And if you want to see a demo, then we can do that after the meeting. Thank you.
Okay, thank you. Next, we have Jeff DLB. Jeff, are you still there?
Yes, I am.
Great. Annie, do we have to do anything to show his slides remotely? We have them locally if we cannot do that.
Jeff, are you ready to share your screen?
Yes, I am.
All right. Okay, you should be able to share.
Okay, can you see it?
We can.
Okay, great. Thank you very much. So I'm Jeff de la Beaujardière. I work for NCAR. I want to tell you about a project that we're working on to put some data on Amazon S3. I'm very sorry I can't be there in person. I was planning to, but I had a minor disaster at my house, and this was the disaster. The ceiling collapsed, so I'm still dealing with the aftermath of all of that. I want to acknowledge a lot of people who've been working on this, especially Anderson, who's been doing some of the data conversion and starting the upload, and then Qifan Shi, who's also been working on upload. Variety of other people from NCAR who've given good advice and recommendations. Some people outside of NCAR, Joe and Anna from Amazon for the hosting opportunity, as well as the other people in our group at NCAR working on what we're calling science at scale. So this science at scale is actually a plan we've written, a draft of a bunch of things we'd like to do. We currently have a supercomputer at NCAR called Cheyenne. We have some local storage, both disk and tape. We have a data analysis and visualization machine. We have some archival data. We have ways to get to the data by the web and to search all the data, and that's all great. But we're trying to do some additional stuff, like starting to explore object storage as opposed to regular POSIX file systems, where we could move some of our archival collections as well as analysis-ready data. Maybe procure an on-premises NCAR cloud to go alongside our regular supercomputer, and then start looking more into things like Jupyter notebooks, Python-based visualization, workflow tools, that kind of thing. And then we also want to send at least some data to the cloud for broad public access, and deploy some of the same tools like notebooks and Python visualization there, but also be looking at serverless computing and allowing people to just bring their own containers and compute what they want in a way where we wouldn't necessarily allow them to bring containers onto our supercomputer, but they can do whatever they want in the cloud. So in this brief summary, I'm just going to focus on what we're doing in the cloud with some of this analysis-ready data. And this is something we're really just starting. So what we have is this thing called the Community Earth System Model Large Ensemble, which is a simulation of climate from about 1920 to 2100, using both observed data for the current and the past time, and then an assumption about greenhouse concentration in the future out for till the end of the century. It's called the RCP 8.5 scenario, which is actually kind of the worst case in the 5th IPCC report. And this data is actually pretty complicated. There's different spatial grids, whether you're talking about land and atmosphere or ocean and ice. There's different vertical axes. We have surface data, 3D atmosphere and 3D ocean data, different temporal resolutions, monthly, daily, 6 hour, different time axes covering various periods of time, which don't overlap very well. And then 40 ensemble members. So this is a large ensemble, which means that numerical simulations were run multiple times, and each time the initial conditions were tweaked just a tiny bit, just at the level of the precision of the numbers. And then you see things evolve differently, and you can start taking means of all these different scenarios. It's kind of like how we do weather forecasting now. You run a bunch of models, and the average is kind of what is most appropriate. So because of all this, the data are currently kind of difficult to access and use. There's about 500 terabytes. Some of it is on disk, some of it is on tape. It works out to about 150,000 net CDF files. You can get to it. We have a thing called the Climate Data Gateway, where you can either download files or even invoke a subset service to get a fraction, so that's great. And if you have permission, if you have an account on our supercomputer Cheyenne, you could actually compute in place using our resources, but most people can't do that. You have to have basically an NSF grant or be an NCAR employee or something like that. So what we want to do is send some of the data to Amazon S3, and we're thankful to the Public Datasets program for giving us an allocation of about 100 terabytes. That's about 1/5 of the total data set, so we selected kind of the most useful stuff out of there. Things we think people will really want to compute on. And as we send it to the cloud, we're not just sending exactly the same net CDF files. We're reformatting into what's called the Tsar format. And I think Rich Signell in the next talk will give you some more in-depth material on that. But basically, we have a number of what are called Tsar stores. Each one is a multi-dimensional data cube. At the moment, there's sort of one Tsar store per variable, but then it gets chunked up in the latitude, longitude, time, and vertical dimension as appropriate. So we break it all up into these chunks. Each chunk is an S3 object, about 100 megabytes in size, because we found that that's a good performance. If you make them too big, it doesn't work so well. If you have too many of them because they're too small, it doesn't work as well either. But in fact, this is one of the things we're going to test, what is sort of an optimum size. And then you can use things like Dask to do parallel reads on whatever chunks you need to actually do the specific analysis you want to do. And there's this Python Xarray library, which will sort of abstract a little bit above these Tsar layers. So you can just say, hey, I want the sea surface temperature, Gulf of Mexico, next 20 years, and it'll just kind of figure it out and read it for you. We're also working on a Jupyter notebook that we would deploy that would have examples of how to analyze the data, so people can kind of start from there and customize as needed. And we'll be setting out some Python-based visualization tools, things like PyVis, but also NCAR has long had a thing called NCAR command language for visualization, and that's being transitioned to all Python. So the current status is this has begun. We had hoped to actually release it in time for the ESIT meeting this week, but in fact we're not ready yet, so we're still working. I think we'll get it released in September of this year. So we've begun the conversion to Tsar, copying to S3. As of today, there's 2 data sets available, the monthly land and ocean data. That's about 1 terabyte, so that's only about 1% of the total data. So we got about 90 to 99 terabytes to go. We may do it by internet, or we may borrow a snowball from Amazon to just ship all the rest. Still debating that right now. But that'll include the daily, 6 hour, and all the rest of the monthly fields. This is going to be on a public Amazon bucket, no egress charges. This is the bucket resource ID and NCAR CESM lens in the US West 2 region. It's not currently public, but if you're interested in taking a look at the data just as kind of a expert user who'd be able to use R without too much hand holding because we don't have all the documentation yet, please send me an email. We can do that on a kind of per account basis. And so we're working on the more complete documentation, the Jupyter Notebook, and so forth. We have a draft documentation page here. This page is publicly accessible, but it's not complete yet. And we're planning for full public release in September of this year. And that is the end of my talk, and I believe I'm well under my 10 minutes, so thank you very much.
Thank you, Jeff. Because you are under 10 minutes, we actually can give you one question if anybody has a pressing question for Jeff. If not, we can save the discussion for the second part. Okay, thank you. Seems like not. Okay, next we have Rich from USGS. Yeah.
I'm just going to take back the presenter. Make presenter. Okay. Share. You bet. This one? Okay.
All right. What's this Tsar thing we keep hearing about? I'm not a Tsar developer, but I'm a Tsar user, so I'm going to give you the Reader's Digest version. It was actually created by Alistair Miles in the beginning, but it's had a lot of folks who piled on, and we were using it heavily in this Pangaea project. In the Pangaea project, as you might have heard, we use, and as Jeff just sort of indicated, we use Dask to parallelize reads to this Tsar data set, and then use X-array and visualization tools to allow you to do everything you need with your big data, and you're just using your browser. And so, originally, this was the use case I was working on, the National Water Model, 15 terabytes of data in a month, and it was pushed out to Amazon as NetCDF files, in hourly NetCDF files. So like for the 25-year reanalysis, that was like 200,000 hourly NetCDF files. And if you try to access those with Tsar in a sort of, I'm just going to pretend this is a file on the cloud. Here I'm reading some data, 23 gigabytes of data, and it takes about 2 minutes to read that data. And if I convert it into Tsar and I read it with the same cluster, it takes 12 seconds. So in this case, Tsar was 10 times faster, and that was kind of the motivation that sent the Pangaea team down this Tsar route. There's a blog post that's really excellent. It's about a year old, but it's still completely relevant today, by Matthew Rockland, if you're interested in reading about some of these challenges and solutions to multidimensional data on the cloud. I'm not going to go into that in the interest of time, but I'm going to tell you a little bit about the Tsar format. So it was, it was developed by a malaria researcher, Alistair Miles, and he knew about HTF, and NetCDF, and he developed this to overcome some of the limitations of what he was seeing in terms of cloud performance. And part of that was due to the numerous requests for metadata that go on before you actually request the chunk of data. And so that thing on those kind of interactions on S3 are kind of killer. You really just want to go and grab the data from S3. So there's a very clear specification for Tsar that's and Alistair is a very clear thinker. If you go and watch his SciPy talk from last week, it's 30 minutes on Tsar, and it's everything you ever want to know, and it's a wonderful talk. But each chunk is stored as a separate binary object, as we've heard, and the metadata is all contained in JSON. So it's very easy to read and find everything you need to know about the data set. And so in these chunks, you can apply filters and compression using BLOSC, which is a C library. And so if you wanted to, even though we've been talking about Python reading of Tsar, you could without too much difficulty, and the NetCDF group actually is doing this, is building other language interfaces, because you can use the same compression libraries, and you can, of course, read binary data and JSON. So it's free and open software, and as we just saw, one of the popular ways right now is to read and write it using X-array. So read a bunch of NetCDF files in X-array and write them out to Tsar. So this is kind of what it looks like. One of the kind of very clever things is that if this is on object storage, the name of the objects themselves is like 0.0 and 0.1, 1.0. These are the different chunk locations. So you don't need to have any fancy dictionary to try to figure out where all the chunks are. You already know where the chunks are. And as I said, each one of these chunks is, you can filter and compress, and then you've just got binary data. This is actually a key, it's also, it's any kind of key value store will work for this. So you can actually use databases, you can use zip files, you can use files on your local disk, and a bunch of other stuff actually. So, and just to show you what this, just to show what this metadata looks like, if you go and, if you created one of these things, you went to your cloud storage and you popped up one of these little files, it would look like this. There's one that's just got the data for the chunk sizes and what kind of compressor was used, with fill value and the shape and stuff like that on the left. And on the right is just like the traditional like net CDF attributes that you think about, like coordinates. These are the CF attributes, right? And then these are these array dimensions, which is actually a convention within Tsar to allow net CDF to work, to have shared dimensions in your HDF. This was developed for HDF originally, but now it works for net CDF 4 just fine because of this little thing highlighted here. There are a lot of compressors and filters in this because of BLOSK, and I'm not going to go into this either, but there's some modern compressors that do much better than the standard ones that are in NetCDF 4, and you can basically double your performance, and with anyway, okay, I'm not going to go into all that. One of the key things I think that actually hasn't been mentioned yet about Tsar is really important, I think, is that it's community driven. So this is, we know how successful open source software projects work, and this operates just the same way as an open source format development. And if you look at the acknowledgements here on the Tsar page, these are some of the rock stars of our community in terms of data. And they're all weighing in on discussion about like where this should go. I think this is super important. So I gave this pretty much the same talk last year, if any of you were here. So what's different this time, Rich? Actually, Tsar hasn't changed that much, which is a kind of a good thing, I think. One thing they have done is they've represented that NetCDF little bit that you have to put in there is not just some weird thing that the Pangaea guys are doing through, with Z array, but there is actually a convention for Tsar. And Unidata, as I think maybe you heard earlier, has formally announced they're developing support for Tsar in the NetCDF C library. And they mentioned today, and I guess I missed the blog post, but they're also developing it for their NetCDF Java library, which would mean that threads and things like Panoply, things like that depend on the NetCDF Java library could be able to read Tsar as well. And as you've heard, actually, here at ESIP, there's continued growth of use within the Pangaea community. Now, I said in my abstract we're going to do some benchmarking. Don't take pictures of this because John Reedy and I have been working together actually to do some benchmarking, but we haven't quite figured everything out yet on the HSDS side. John's going to tell you about HSDS in a second, but essentially we would like to test. So Tsar works great, but there's the potential that HDF5 files, NetCDF4 files could work just as well if we did some preloading of the metadata and then did parallel range gets into that object. Now, John actually is going to tell you about how he does that on the back end of HSDS, but I'm interested if we could pull that functionality out and actually do that outside so that, again, we would not have to do it through a service. Some people might want the service, but some people might want to do it outside the service. Anyway, these are what we've got so far, actually just comparing. This is just one use case, okay? So I compared Tsar and S3 access through the new capabilities of the H5Pi library and to actually go right to S3. And so this is just comparing basically the exact same data set with the same chunking, filters, and compression, and just one simple test. But on the left is 4 CPUs, and then 8 CPUs and 16 CPUs, and the timing on the is y-axis. And so when you've got 4 CPUs, Tsar is the fastest, but HSDS is not too far behind, and S3 is quite a bit slower. It's not 10 times slower though. It's only like, in this case, so it's use case dependent for sure, but it's more than twice as slow. And when we move to 8, Tsar and S3 are actually scaling pretty well, but HSDS currently doesn't seem to be, and so that's what we're kind of looking into. And then when you go to 16, S3 hasn't gone down quite as much, but Tsar kind of is scaling as you might expect. So basically, the more cores you throw at S3, it pretty much scales linearly. I mean, at Tsar, you pretty much scale linearly. One additional thing that I just wanted to mention that's kind of cool that Ryan Abernathy announced at SciPy was that he realized that you could just take your Tsar data set and put it on your own web server, like just your Apache web server. And actually, that works. And so I compared the exact same file to my OpenDAP server that I had. So I just stuck it on the same server where I had my OpenDAP server. I stuck it also on the website. And if I throw 5 cores at that, it actually outperforms my OpenDAP server, which is Thread. Sorry, it's my Thread server. I should say Thread server. So, and it's probably a lot more robust than my Thread server. So anyway, so that's it. If you are interested in Pangeo, please come join this conversation. There's a lot of interesting conversation about all sorts of things surrounding this whole area over on Pangeo GitHub. Everything's discussed out in the open as GitHub issues. And if you want to, and if you're interested in Tsar, please watch Alistair's talk. It's already up on YouTube, and it's a fantastic talk. So thank you very much.
Thank you, Rich. Next, we have John with the HDF group. Let's see, where's yours? This one, right? Oops. I was doing that before. There you go. Thank you.
Hey there. So I'm going to talk about HDF and the HDF server and how that's all connected to what you've been hearing about Tsar and the cloud and such. So the HDF format, it's been around for 20 years. It's developed quite a bit of infrastructure. There are libraries built on top of it, like NetCDF. There are archival storage of HDF5 data that's in the petabytes. It's used by NASA for all their instrument data and so on. But as many people have talked about, HDF5 in the cloud is not always such a happy marriage. The way HDF5 is stored has worked well for POSIX file systems, but doesn't translate so well for S3 storage and other object storage systems. So we started working on developing a server and an alternative way of storing HDF5 data that's meant to be designed for the cloud. So this is HDF server. So this was sponsored by NASA as an access project. It's open source, and we call it HSDS for Highest Scalable Data Service. And the features of it are it runs as a set of containers. So some of the challenge we've heard in other servers of scalability, the intent with HSDS is that you can scale to any amount of throughput by increasing the number of containers. Each request can be parallelized across multiple containers. And this can accelerate many common operations. It's feature compatible with the HDF library, supports reading and writing of data, and uses S3 as a data store. And existing HDF5 APIs, yes, it's exciting. Existing HDF APIs like H5Py and H5NetCDF, Xarray, et cetera, can work without change accessing the HDF server. So this means all your existing applications don't need to be rewritten to use some newfangled thing. They can just start working. And we developed a Jupyter Lab environment called Kita Lab that gives you Jupyter plus access to a server. So you can go on there right now and start playing with the server. And also we have an AWS Marketplace product called Kita Server that people who want to have like a one-click install of their own server can just go to. So the idea of the schema for the HDF server is much like the Tsar format. One of the biggest differences is whereas Tsar, they use periods to delimit the chunk keys, we use dashes. But otherwise, it's similar in intent, in that each chunk in a HDF5 dataset is stored as an S3 object. So when clients are doing a request, say this yellow rectangle in the middle, they send that request to the server. The server figures out which chunks are needed to serve that request, and then it can spin out each chunk extraction to a separate container. And those containers in parallel can be reading from S3, getting the data, uncompressing it, segmenting it, and then returning the joined region back to the client. So when I experiment with this, it's often the case that it's faster to access the same data through the server than it is to access that data on my local computer, because we have this advantage of the server being able to parallelize requests, especially ones that traverse many chunks, which, for example, is often the case with like time series extraction. Here's an example of what the metadata looks like. Again, it's very similar to the Tsar format. So schema details, this year I did a reorganization where now the objects are organized by the root ID of the object. And this was driven by a change Amazon made last year. They raised the S3 storage node limit from 300 requests per second to 5,500. And this meant that formerly you wanted to spread out your keys over the bucket so you wouldn't overload by accessing the same key prefix multiple times. Now that's not a big deal. So we can simplify the organization. The schema I developed was for the use of HDF server, but as Rich pointed out, there's no reason that clients couldn't directly access the data in S3. It's JSON and binary blobs for chunks, so it's fairly simple to write your own software to read that. A bunch of new features over the last year. Now we support accessing traditional HDF5 files that are stored in S3, and I'll talk about that in the next slide. We have more filters. We have fast metadata loading. So oftentimes you have clients who are reading a lot of different metadata, and that means a lot of round trips to the server, and that latency can add up. So we have an option where you can pull all the metadata down in one request, and then it can be cached on the client, and that's very fast to access afterwards. H5 NetCDF and X-ray support is there now, variable length data, and the schema changes I talked about. So, you know, Jeff talked about this effort to store their data into Tsar format and how they didn't get all the data they wanted to for ESIP. Because it's a big job, right? Because it's a lot of data movement, it's a lot of computation to translate that data to a different format. Since we have these petabytes of data now in S3, wouldn't it be great if we could just access those data with all the benefits of something like Tsar, but without having to change that data? And that's what we can do. So what we do is, as in here, on the right, we have an HDF5 file. The chunks of each data set are located in the file. Well, I want to say randomly. Well, it's not random, but it's unknowable to the outside person. But we can mine all these chunks and create a map of where those chunks live within the file. That and other metadata in the file is extracted from the file, and the server keeps that information. And then when we read dataset data, the server does range gets to the original file, pulling out just that chunk and then uncompressing the data and then the pipeline works just like normal. So this means that if you have a file, you run a script to extract the metadata, that metadata is a fraction of the size of the file typically, like maybe less than 1% of the file. And then performance-wise, it's equivalent to as if you had done the full sharding of the data. And I would suspect it's equivalent to what you would get with Tsar. Finally, I want to talk a little bit about Kita Lab. So it's a Jupyter lab on Kubernetes. You have access to the Kita server, and it's free for users to come and try out. Nice thing about Kubernetes is that it's this common platform. You have your containers, and you can expand the amount of compute you have to meet your needs. So here's how the whole thing works. You have the user going to Jupyter Hub. Each user gets a container. The container runs basically one core of CPU, but that user can access Kita server, which has multiple nodes. So you're in effect being able to access multiple cores of compute at will. And I have a bunch of references for people who want more information. Thank you.
Thank you, John. Next, we have Otis and Jonathan from North Carolina State University. And I'll let Otis explain the acronym of his new organization. Well, it's not a new organization, it's just a new naming. Okay, let me see. It's yours right here, first one. Awesome, okay, thank you.
So now I get to have this. Okay, we're going to give you an update now on the big data project, Data Broker. Some background, many of you may not know what the NOAA Big Data Project is. I hope all of you do, but it's been an experiment with industry via CRADA agreements. There were 5 separate ones that was extended to May 2019. The arrangement with the government was industry provides access to NOAA's open data to all users. Data remain open, they're not sold, and the collaborators monetize services based on data. It uses open data to combine sort of 3 powerful resources: NOAA's science and subject matter expertise, industry's data storage and cloud expertise, and industry's tools and processing. Their award of a recent RFP for commercial follow-on services is in process. So you might wonder, well, what's the data broker? We're kind of the impedance matcher between NOAA and the public cloud providers. And so it was up to us to try to understand, what did the public cloud providers want? When did they want it? How did they want it? And to make it happen. That's what this slide basically says. There's also resolving operational problems, data integrity issues, some certification of cloud partner holdings on demand, and adding new data sets. These operations, and Jonathan has been the primary person doing this, had to do with resolving source and destination outages, things about transmission challenges, 24/7 operations, and new data sets, as I noted before. I'm going to show you an overview of about, I think it's 14 data sets here. Total broker data sets, this is just being moved by the Cooperative Institute right now, is about 5 terabytes a day. They come from a variety of NOAA sources you can see on the right. Whoa. You might wonder about ranking, what's the access to these data sets? On the left is by numbers of access over the period of record for each data set, starting with GOES 16 down to the global ensemble forecast system. and on the right is by volume. Similar ranking. I'm not going to really go into this in any detail. I'll talk some more about some specific accession rates on AWS for these 14 data sets, which is about the period, I'd say that's maybe 15 to 18% of the total public holdings. So it's kind of a snapshot where we have insight into what's going on. This is by accession rates. You can see that it started out last year at about this time. It was sitting something, I think, at about 20 million a month. It's gone up to something like the 40 to 50 million a month accesses now, with peaks that go way above that. If you look at volume, you will notice that we were talking last year something like about half of where we are now, with some noticeable bumps as things have gone along. For example, just last month, there were 900 terabytes of GO 16 and 17 accessed on AWS alone. The increase, the trend is about 16 terabytes a month if I don't look at the June number. So in other words, that's the steady trend for these two data sets. If you look at specific things, from the government's perspective, one of the questions is, in effect, what's the ratio of bytes that are accessed on the cloud versus what goes into the cloud? So the y-axis is the multiplier. So you can see last year we were somewhere around 10. Now we're probably in the mid-20, around 20, with jumps to something like 40 in June. So, and the point of this graph is this sort of variance happens without any noticeable impact on user access. If you look at accession ratio for GO 17, this is a much newer data set. You can see, as with GO 16, it starts building, but June was a special case for it as well. So we wondered, are users really interested in, so we split this by type, and as you'll notice, the top line on the graph is by radiance, and then you've got the sort of cloud moisture imagery. Level 2 products and lightning is on here just to give you an index of how that, when it was turned on, and what's been happening since with the lightning mapper. But you can see that there's definitely a preference for level 1 data from Amazon, and there's a preference if you look for full disk. So of the various GOES types of data that are being accessed by users. Now you might wonder, what's the temporal nature of this access? This is showing, it's a combined graphic for GO 16 and 17, again on AWS, starting for when GO 16 was turned on in 2017. And you notice that if you look at the daily frequency, data that's less than 5 minutes old has about 50% of the accesses on any given day. On the other hand, about 25% of the accesses are over 24 hours. So there's a significant continuing archival access to this data. That's kind of a surprise. But you also notice these dips when the greater than 24 hour, these are in effect where somebody has decided they want to do an archive get, as in June, where someone we guessed said, let's do 900 terabytes of data. Final 2 slides. First is GO 16 access. This is somewhat of a surprise. Please understand that GO 16 goes east, so it's the Western Atlantic, Eastern and Central US, North and South America. So the Americas access is a given. What is the big surprise is when you start looking into the Middle East and Eastern Asia, other places. This is a broadly accessed data set. This was a big shock. Not such a shock as the global historical climatological network, an NCEI product. You can see that this has global access. And if you looked at the accession chart, this is like number 5 or 6 on the chart. This is a surface data set. We expected global access, and that in fact is what you see here. Thank you very, very much.
Okay, great. Thank you. And the last talk is by Joe. We have a few minutes, so he offered to squeeze it into 5 minutes.
5 minutes?
Yeah, we have 5 minutes.
Well,
So
that's really impressive.
this is outstanding. I really appreciate that everybody kept the schedule. So.
Thank you, Annie. Thank you. All right, hey everyone, I'm Joe. I work with Amazon Web Services. I'm on our open data team, and I oversee some of our public data sets. So keep in mind, I work helping people figure out how to optimize their data for usage in the cloud. So I think I'm here partially as comic relief to take us into the break. But I'm going to tell you why maybe you don't always need to optimize your data. That's what I was asked to do. So I will do that. So I'm going to skip over these first couple of slides because everyone else has already talked about cloud optimized formats. I will slowly skip past them while I talk so that you know that I put a lot of effort into copying them from another presentation. So the one thing I do want to tell you though is part of the reason, I guess in some seriousness, part of the reason why I'm talking about this is because like all the stuff that everyone talked about, while it's super valuable and there's likely very good reason to do it and times to do it, it's not easy. Right? Like, I don't know that anyone stood up here and told you that that was all very easy. So you want to make sure that you're doing it for a good reason. And if you're optimizing too soon, that's generally not great, right? So I'm just going to sort of talk through a different type of data. So it's actually the GHCN daily data that Otis referenced, but this is tabular data, right? So it's not raster data, it's not multidimensional data, it's tabular data, which is a little bit easier to think through. So I'll talk quickly through two different sort of optimization vectors. And again, this isn't going to look like some of the other things that we saw with Tsar or with cloud optimized GeoTIFF, since this is tabular data. So the GHCN data is very easy to think about. It's a whole bunch of weather variables for a number of stations, right? So like it's tabular data, so it would look good in a spreadsheet. So the examples that I use are going to use a service that AWS has called Athena. But basically, this is writing SQL queries, right? So that's a SQL query that's right up there. Don't really worry so much about the service, but I guess it will come in a second. It's just an easy way to illustrate how much data is being scanned at any time, right? So I just did somewhat of a pretty cool query against the data, which, I mean, I guess as an aside, it's very cool that you can do this at all. So all the data is made available in the cloud, and you can just write a query like that. And I think there's a couple billion of these data points, 2 to 3 billion of these data points, and you get an answer pretty quickly, right? So how quickly can you get an answer, and how much will it cost you? So this is where the Athena part comes in. Athena charges you per amount of data scanned, right? Which is another thing, like, are you optimizing for time or are you optimizing for price, right? So the table is there. If it's just the CSV data, which it is made available as, to do that query, and again, this is going over all of the data, it took 70 seconds to complete, which, I mean, that's kind of cool, right? It scanned all of the data that was available, so that's close to 100 gigabytes of data. The data is also made available gzipped. Just as an aside, gzip is not the same as zip. So gzip is generally more cloud friendly. A lot of cloud tooling can work with gzip. Maybe I'll put it that way. Thank you. It can't necessarily work natively with zip. So just if you're compressing your data. So this will compress it. So you see the time it took to go over the whole thing was much longer, but the data scanned was much less because it's accessing compressed data. So if you're optimizing for price, you might want to gzip it. If you're optimizing for time to get your answer, you would probably want to not do that. Now, there are cloud optimized tabular formats. Parquet is one, ORC is another. So it's very easy to create these, sometimes with an asterisk. So then you would imagine that if you're scanning that data, it goes much quicker, which it does. You can now get your answer in 30 seconds. And the data scanned was under 9 gigabytes. So it goes much quicker if you do use something that's cloud optimized. But the point here is you do not have to. The tool, and this is true for most tools, will work on top of any way that you're providing the data, assuming you're using something reasonable like CSV in this case. So If we looked at a simpler query, so this is just getting the count, you can see the similar times there. The one that I do want to call out is this is where a cloud optimized format can come in handy. Parquet, it pre-generates this count for you. So you see, you get your answer back in 2 seconds, and it actually scanned no data because it didn't need to hit any of the data because it was pre-calculated. So this is where something like a cloud optimized format can come in handy, depending on what sort of queries you're running. So just one more to give you an idea of a different data set. This is a data set that we made available with Facebook. This is actually from NASA DAC season out of Columbia. So this is a high resolution settlement layer. So it's population data around a bunch of different parts of the world. But here we're optimizing in a different way, right? So we're actually trying to scan less data. So the data is just made available in gzip CSV. So we're not compressing it at all. But what we're doing is we're adding query filters. So it doesn't have to filter, or it doesn't have to query all the data, right? And so this basically looks like keys. And so you have a key that says country. And so when you say country is CHO, which is Chile, it will only access the data related to Chile, right? This is a very database-y type thing. But again, this isn't a database. These are just flat files sitting on an object store, right? And if we say Chile and we only want folks that are 60 plus, which they call elderly, I'm not making that decision. That's what Season said, so blame NASA. I guess I do have a NASA shirt on, but I work for AWS. So it will only scan a very small amount of data, right? And this is, just so you know, Athena pricing, that 0.016 gigabytes is many, many fractions of a penny. So you can do these sorts of analyses very, very quickly. And again, these sorts of optimizations are very easy, but if you do not need to do them, you do not need to do them, right? I think that was the point of what I'm supposed to say. You can work with a lot of these things with non-optimized data. The tools will just work better for you if you start doing optimizations, but it's not to say that you need it to be optimized from the beginning. So with that, I will stop, and I think we're right up against the time. Thank you.
Thank you, Joe. Great. So thank you first of all for all the speakers. I really appreciate the contributions and the fact that you stayed on schedule. Just to summarize the next step, so we're going to take a break now for about 15 minutes, I believe. And then we're coming back and we're going to have more like organic, informal discussion about some of the things we heard. And also, I'll put up the questions that I showed you initially, but just to think about what we listened to in the last hour and a half. We had a bit of an eclectic set of presentations covering anything from, you know, data providers to data users that are trying to leverage data in the cloud to provide services and derive insights for the community. We were looking at model data, in situ data, and remote sensing. And we also heard about optimizing metadata, services, formats, tools. So as you can tell, that the breadth of this conversation is definitely big, and that's what makes it so complex, like many of the users, the speakers mentioned before. So keep in mind all of this, but the goal for the next part of this workshop is really to think of what are the things that are emerging that seem like best practice that we can start to adopt and share with the community. Do we need to think differently when we're thinking of different data types, when we think about modeling data, remote sensing, or in situ? Do we have to treat them differently from the perspective of bringing data to the cloud? But how can we make it seamless from a user discoverability and usage point of view to make all these data sets available in the cloud? So anyway, thank you, and I'll see you in a few minutes if you're interested in continuing with us.